Hi, in this video we are going to demonstrate the Fronthaul Testbed that we are developing here at UFPA for investigations on the use of Ethernet for the Fronthaul. So this video is going to be composed by two main parts. In the first part we show the infrastructure for clock synchronization in the Fronthaul, and the second part shows the setup for evaluating the Fronthaul together with an LTE base station based on open source software. So the first part of this demonstration will show the clock synchronization. We have here a testbed with 3 FPGAs. One of them represents a baseband unit and the other two are remote radio units that are served by the BBU over Ethernet. So we have a switch connecting them, and we have 3 hops between the baseband unit and both remote radio units. And PTP traffic, the precision time protocol traffic, goes alongside the Fronthaul traffic. So they go over the same links over the Fronthaul, and PTP traffic therefore suffers from delay variations due to contention together with the Fronthaul traffic. Okay, so let's start by showing the best solution that we have currently for synchronization. So we have here our PTP algorithms operating, and in the VSA we have very stable QAM constellations. So we can see here, first of all, that the constellations are showing an EVM of approximately 1% RMS, and of course we are connecting the RF interface directly to the VSA through a cable. And another thing that we can see is that the RF spectrum is being centered exactly at the nominal carrier frequency, in this case being 2.45 gigahertz. So the reason why it is centered in the nominal frequency and the VSA can track the constellations is because the frequency synchronization accuracy is good enough. Another aspect of the clock synchronization is that this allows the buffer levels to be synchronized between the BBU, the baseband unit, and the RUs, the remote radio units. So in order to understand, let's go quickly on how this should work. So the idea is that we have a baseband processor, and the baseband processor is first introducing the IQ samples into a buffer, the TX or transmit buffer. And these IQ samples are first stored using the sampling clock, and then they are read from the buffer towards the Fronthaul using the Ethernet clock. Okay, so these IQ samples go then through the Fronthaul in the Ethernet frames, and when they reach the receive end, they are first stored into another buffer, the RX buffer now, and they are stored using the Ethernet clock. And then finally they are read towards the RF interface using the sampling clock. So the main constraint that we have here is that we need both sampling clocks, the one that is generated at the BBU side and the one that is generated at the RU side, to be matched. If we do so, if they are matched, then the occupancy levels at both buffers are going to be stable. So that's the idea. We need these occupancy levels to be stable in order to prevent underflows or overflows. So we have here a real-time plot of the occupancy levels at both remote radio units, and we can see that both of them are around the center of the buffer. So these buffers have 512 positions, and both occupancy levels are around the midpoint, around 256. So this is again a result that comes from the fact that the sampling clock is being synchronized at the RUs with respect to the baseband unit. So now that we saw the performance with PTP turned on, we want to show you what happens when PTP is actually turned off. Alright, so I'm going to turn off it right now. Now that it's turned off, the first thing that we see is that the constellation is not being tracked anymore, and the reason is that the RF spectrum is now centered in a frequency that has an offset with respect to the nominal value. So we can see here that the constellation is not appearing, and if we observe very carefully here, we can see that the RF spectrum is slightly shifted to the right, and that's because the RUs are now generating their carrier frequencies with the natural clock frequency that comes from their crystal oscillators. So the carrier frequency shows the same frequency offset that their oscillators have as well. So even if we set the VSA to these carrier frequencies that are offset from the nominal value, there is one more problem, is the fact that the buffer levels won't be stable. So we will have some underflows and overflows, so we have data corruption. Following the sequence, what we want to do is show what happens when we turn back PTP on, but we do so only using the standard PTP algorithms. So the very basic equations for estimating time offset and frequency offset. All right, so we want to do that right now. So after some transition time, with the standard PTP algorithms, the carrier frequency at the nominal value can still be tracked. But if we observe the constellations, we can see that they are very frequently rotating because the frequency corrections are very abrupt using those basic equations. All right? So we see that the EVM is very frequently corrupted and the constellations are lost in this process. All right? But the RF spectrum, again, is centered closely to the center nominal frequency. Now, if we look into the oscilloscope, we can see that the alignment between the two clocks is very jittered. So the corrections are very abrupt, and we can see that the rising edges between the two clocks is changing very fast. And that's a problem because it introduces phase noise, and that corrupts, again, the constellations. So now, the last step is to turn back on our algorithms for synchronization and to see how they solve this problem. All right, so now our algorithms are turned back on. So first of all, they follow a transition step in which the delay estimation is first acquired, and then after that, the frequency synchronization is better achieved, and then the accelerator step, the time synchronization will be precise and stable. So let's see that. All right, so after the transition, now our algorithms are tracked again, and we can see that the buffer levels have transitioned from close to the underflow section back to a position in which they are closer to the midpoint of the buffer. So if we inspect the constellation now, again, we see an EVM of around 1% RMS, very stable at that value. And the reason is because the buffer levels are stable enough and there are no data corruptions or data slips in the buffer, such as overflows or underflows. All right? So again, the spectrum is centered at the nominal value and the constellation is stable.
So now let's switch to another scenario we are working on. In this scenario, the LTE signals are generated in real time. So in the previous scenario, the LTE signals were recorded or generated by MATLAB, recorded in the memory, and then read cyclically and sent through the Fronthaul. But in this scenario, we are actually generating the LTE signals in real time by a software called Open Air Interface, which runs in a separated CPU, and the CPU communicates with our baseband unit through the PCI Express lanes. And with this setup, we can evaluate how the Fronthaul impairs in the LTE protocol stack. In the previous setup, we were using cables to connect the remote radio units to the VSA, but in this setup, we choose to connect them using the wireless medium through these antennas. And also, the user end can get these signals and send it to the baseband unit over the Fronthaul. So here we can see the time domain signals, the frequency domain, and the constellation of the demodulated signals, along with some EVM results. Here we can see that even with the wireless medium, the EVM keeps around 1.5% RMS, and also the synchronization is occurring very well, so the signal is centralized, and the constellation is actually well defined and stable. Finally, we can see in the time domain that just the control signals are being sent over, through the downlink, because in this case we don't actually have a user end connected to the base station, but you can see that the signal is being very well transported through the front haul.